Okay. So, why is my Why are you being so different? No, I don't want to go that direction. I want to go the other direction. So this is 111. Yay, you made it to 111. Awesome. Not only are you here in terms of you made it to 110, but you also made it through and got to this room today. So yay, that's awesome. As far as the introduction goes, my name is Dr. Annette Hartley. Please call me Ann because I'm not tall enough for all those letters. So I did my undergraduate degree at UC Riverside in BS in chemistry. I also have an MS and PhD from ASU and did a lot of teaching while I was there. I taught at ASU, I taught at UA, I taught at community college because that was kind of to be expensive community college. I taught at Iowa State when I was there for the brief second that I went. And then I have been teaching here on and off since 2012. I started here full time last May, so it's almost a year now. And hope I end up staying here for some time. My office is in the 970 building, 302L. It's a locked hallway. So if you need to come talk to me, you'll have to call my extension. It's posted at the end of the hallway, and I can come and let you in. It's to protect us from crazy people. My office hours are going to be Monday. Those are my home. I'm sorry. So Monday and Wednesday, right after class. So if you have class questions right after class, I will be available between now and lab. Okay. That will be on the third floor. There's a room up there for 307A that I will be in. For that, I also have the entire day Tuesday available for office hours, be they virtual, in person, whatever you guys want to do. And if those times don't work for you, I'm happy to meet with you. That's whenever that's a good time for you. My phone, 843-546-6699, and my email address, the one that's not through D2L, is there as well. I do check my D2L email only during the week. So if you email me on the weekends, you probably won't get a response. But if I happen to be in my computer, I may respond to you. As far as that email goes, that comes to me directly to my phone. So anybody who emails me there will probably get a better response. So there's that. Questions about any of that stuff? Okay, that's the fun part. So now here's the part that I really like. You're gonna do it, aren't you? But you're gonna be difficult. So I want to know who you are. It's important for me to know who my students are so that I can understand how I can work best with you guys. And of course, it's fair for you guys to have questions about who the heck I am. So this is what I like to do in our little introduction. You're going to need to start to learn to talk to each other. So this is a good way for us to do that. I want to know what's your overall goal in being. Yes, somebody told me your butt had to be in this room. Okay, fine. But why? What program is it that you're looking at? What are you trying to transfer to? Do whatever that is. That helps to inform me about how I can approach you and explain things you may not understand. So I want to know why you're here. What's your major / emphasis? Do you like math or do you not like math? Because if you're not comfortable with math, then there are different ways to explain things to you. But if you're mathematical, that's the easy way for me. So I can work with that. Okay? I can do both. And then there's this thing right here. Yes. You get one word to define you, to all the other people in this room, and to me. So I'm going to start with my word. I can be stubborn. Why do I tell you this? Because occasionally I get off on a tangent and I'm not necessarily paying attention to the question that you're actually asking me. So I'm focused on what it is I think you're talking about, and I'm not necessarily hearing. It's okay to tell me, well, man, take it down a step. It's not cool. Stop. That's okay. But I want to know how you guys are define yourselves. I find that doing it this way is really my insight into who you are. So as you introduce yourselves, I will be taking a few notes that will stand as our attendance for today. After today, I will have an attendance sheet that I will pass around for you guys to sign in so that we can make sure that you're here. Yay, because that's the thing. So who's my first victim? Volunteer. Go, awesome.
My name is Gabby. My overall goal is to finish my associate's degree. And then I'm debating whether transferring to a school to do software engineering or transferring to a four-year college and finishing my bachelor's degree.
Mhm.
But this is my final class of my associates, and I'm very excited about it. I like math a lot. It's my favorite subject, and one word to describe me is discipline.
Awesome. Thank you. Who's next?
Okay.
Go ahead.
I'm Nick. My overall goal is to be an electrical engineer. This is actually my last class also before I transfer over to Citadel and apples or oranges. And I would say I'm a night person, not a morning person.
Interesting choice of class time. Awesome. I get it. Yes, thank you. Appreciate it. All right, who's next? Okay.
Shelley. I'm here because I'm retaking all my undergraduate classes to apply for my master's in physician's assistant studies. I like both apples and oranges and math. I think they both go together. And a word to describe me would be perceptive.
Nice. Awesome. Thank you. Who's next? Go ahead.
My name is Gino. My goal is to finish out here on my prereqs to transfer to a four-year to get my bachelor's of science. I like math, but I also like I don't know how my brain works. So I simplify stuff. I'm a visual learner, so I like to see how things are done and what I can process that. And then we're describing I'm pretty patient. Yes.
Awesome. Thank you very much. All right, who's next? Go ahead.
I got my bachelor's in acting training and teaching place for school. I guess I'd probably do apples and oranges. And I would describe it as adaptable.
Nice. It's a good one. All right, who's next? Go ahead.
My name is Gabby. I'm hoping to get my associates in science and transfer to Chicago. I don't know where yet, but I'll figure that out. I don't like math, and I think a word to describe me would be understanding.
Excellent. Thank you. I think I have one more.
Davis. I'm here to do mechanical engineering. I'm actually a senior in high school with Berkeley Middle College. And after this, I'm going to do the 2+2 thing. I'm okay with that. I like physics so much, I do it. And
Oh, thank you. It's magnetic right there in that corner. Thank you.
I'm pretty laid back. I can work with anything.
Awesome. And what was your word? Laid back?
Yeah.
Okay. Just sorry, I got interrupted. Okay. Awesome. Thank you very much. I appreciate you giving me some insight into. So some of you know me and how things go. So I am pretty casual about how things are. If you have questions during class, don't hesitate to ask. Not a big deal. Just because I understand what I'm saying doesn't necessarily mean that other people do. What else are we going to talk about? Well, let's see. The syllabus for the course has been uploaded to D2L. I have put up a scavenger hunt exercise for you guys to guide you through all of the course documents because there are 8 billion of them. That is due by the 12th. Okay, so that's the scavenger hunt. Any acknowledgement quiz is due on the 12th as well. That's just to say, yes, I read all the documents. Woohoo! And all you have to say is, yes, I read it. It's just a yes or no kind of deal for that one. The scavenger hunt, on the other hand, is meant for you to find specific information that's relevant to the class. Please understand that this is not, while you get points for doing it, it's not really meant to be graded. Okay, so if you get the wrong answer, it will tell you what the right one is, just so you have that information. Those are things that I thought were really important out of what we were going to need to know. But here's the other thing. If it says it in the syllabus, I can't change it. Okay, so the material that's supposed to be covered has to be covered. We need to make sure that all of that is covered in the way that it's supposed to be, whatever that means. And there's one really big thing that it says in the syllabus. There is no extra credit in this course. Now, while that is said, please understand that I have this policy called redemption points. So when we take exams, I give points or opportunities to answer questions that are not graded first. You can get points for them so that if you screw up something else, that way you can get a better grade on the test. Because I know I've taken tests where I'm just like, I have no idea how to answer that question, and now I'm screwed. I don't like it. So you will see that there are redemption points available on the test. That is available to everybody at the same time, so that is an acceptable thing for me to do. But other than that, there is no extra credit. Questions about that? Yay. Yay. Now I figured it's the first day, right? We want to talk about a ton of stuff. So why is all of this up here? Because you came into this room with the expectation that you already took 110. So all of that stuff is supposed to be in your head. I understand that that may not actually be the case. Right? That's perfectly fine. Today's lecture is meant to give you some idea of what you're going to need from 110. If you don't have it all, that's okay. We can work together. We can figure that out. All right. But if you don't remember some of these things, that's an indication to you that that's something you may have to work on. And of course, the expectation for the chemical equilibrium lecture that we're going to talk about on Wednesday is that we pick up exactly where we left off from 110. So there is an expectation that all of that is there. So we're going to be talking about the stuff that we talked about at 110 that is directly relevant to what we're going to be doing in the So this lecture is for. Is there any formal homework for this? That's the other thing. Is there formal homework? That's Alex. So you will have to sign up for Alex. That's part of what you do in the scavenger hunt. Alex is an online homework system. It does automatic grading for all of your homework. There is an assignment that goes with every topic that we cover. Okay, and that is listed in the schedule. That is the only part that's graded. You will see a bunch of other stuff on D2L practice that we have available. Those practices are for you. So there's in-class practice, stuff that's just meant to get you to understand those ideas. And then there's what we call the after-class practice, of what I call it, which are questions that I have written that directly reflect what you may see on the test. Okay. I have, in the past, taken my questions, all of them, for a test directly from those questions. Because if you bother to do all the work for that, then why shouldn't I give you some points for having that? So those questions are meant to be a guide for you in terms of what questions I'll ask. Questions about what actually is in all of that. As far as what is actually going to be graded for this class, let me see if I can pull up D2L. That was not what I wanted to do. Because what I decided to do is anything that is going to be graded will exist in one place, because I thought that might be helpful. Come on. Work with me here. And so everything that's going to be graded for the course, you will see in the assignment section. This will have a link to whatever it is that's due. You'll see that there is a breakdown of stuff for the lab. We'll talk a little bit about the lab today during the lab section. But everything that gets points is in this list. This is a very long list, so if you've got this listed to 20 items, you're not going to see everything. So you'll need to go beyond that. I think there are actually 52 things on the list. So, but that's anything that you will get a score for. That way you know everything that's there. All right. What you'll see in terms of the labs, which I'll just briefly mention at this point, is that there are several portions for each lab. There's a summary and pre-lab that goes with it. There's a lab notebook. There's the post-lab. And for some of the labs, there's the Excel spreadsheet. Okay, not all of them have. So if those things are required for those labs, you'll see them here. There's also a checklist that's available for every lab so that you can see what needs to be turned in. And we'll talk about, like I said, we'll talk about that when we talk about the lab board. Question about any of the, what's going to get graded? I know, I jump around a little bit, I apologize. So these are the things that we're going to be talking about today. Is the stuff that's going to be directly relevant to what we're going to talk about in 111. We'll talk a little bit about how I do math. Okay? Because if you ever taken class with me, you may not understand what I'm doing. A little bit about problem solving and how that's going to work, a little bit about test taking and assessing. So those are the things that are outside of direct chemistry topics that we'll be talking about. So math setups for chemistry. Yay! So two things. One, I use something called a factor label. It means you will never see a number that doesn't have a unit. Those units are important. Okay, so I need to make sure that they're there. So I need to make sure that they're there. One of the reasons that I do this is that if I cancel this unit, if this is on the top, this is on the bottom, the grams are going to cancel. If I cancel all of those units, except for the one that I'm looking for, then unless my calculator throws up while I'm using it, the number that I get should be accurate for what I'm trying to calculate. So that's helpful to me to try and make sure that I've set things up correct. When I work problems, you'll see me do this. I would sometimes go, okay, I need to multiply, no, I need to divide, because I know that the units aren't going to work if I don't. So that's why I teach you to do that. The other thing is I use this train chart. This means that everything's written above the line is multiplied, anything that's below it is divided. They don't necessarily go together, it depends on what we're calculating, whether they do or not. In terms of what things are, I will try and tell you what each term means. Okay. So this is the mass of the NaOH, that's the volume of the water that we use. This is the molecular weight of the NaOH, the molar ratio of HCl to NaOH. And that's the molarity of NaOH for this calculation. Okay. So that's something about how I do the math setups. Questions about that? I will not always have the written all out here. I do intend to work some while we're doing this, but I need to make sure that I have that for you. Okay? In terms of problem solving, for me, problem solving is a big part of what we need to be able to do. Okay? So you get this big, huge question that has all these words and all these numbers. It's like, oh crap, what the hell am I supposed to do with that? I don't like to look at the words. So I tend to do this very systematic. I will write a balanced chemical equation for whatever I'm doing. I will put any information that I have about those species with that. So, for instance, if we're talking about what we were talking about before, and we knew that we had this 0.26 molar HCl, I would take my balanced equation and have above the HCl that concentration. Concentrations and volumes tend to go above those things. Molecular weights go below. I calculate molecular weights for everything. If I don't need them, just because I only want to do it once, then I don't want to have to worry. The most annoying thing in the world to me is to get partway through doing a calculation and go, crap, I need to calculate that. So I always do that. So molecular weights below indicate what I'm looking for. So which of those things am I trying to find? And then I set up the math. This is a consistent thing that I do, because that makes it easier for me to figure out what it is I'm supposed to be doing. So again, you'll see me when I work problems, this is how I set things up. Okay? And I hope that that will help you to do that. And this setup that we're talking about here, actually, see, the NaOH plus the HCl, this is the NaCl plus the H12. Molecular weights are all down here. I have 25.368 grams and 3.5 liters. I have 0.026 molar HCl. I want to know that volume. Okay. Questions about that? Sweetness. Oh Lord, it's a ton of words. Right? Why are there words? Because why not? In terms of test taking, I just want to give you guys some pointers, because I used to teach test taking all the time, that especially when we get to 111, especially on the 111 assignment, which I know, right, and not responsible for that. There's way too much stuff on that final for you to be able to apply at all. It's designed that way. So if I can give you some techniques for how to deal with that beforehand, that's helpful. So some of the things that I typically look at, I get my test, I look through all the questions, how many questions are there, how long do I have for this thing, that kind of thing. I can do some mathematics, approximately how much time do I get for each of these questions. Are they all going to take that amount of time? No, that's good, because then I have time for other things. One of the other things you need to look at is point value, because if you have one question that's worth 80 points and a bunch of other questions are only worth 20 points, then maybe it saves more time to do the 80-point question, and we should do that first. My next strategy is to just go, is there anything that I know how to do right this second? Because that gives me confidence for everything else. And then there's is there anything that I have no idea what you're asking me about? Because then I can mark that and go, let's look at that last, because that's going to screw with Mike. When you're talking about multiple guess, I do call them multiple guess, I would eliminate anything you can first. So if you know that there's something wrong with that, get rid of it. For anything that's left, if it's still a possibility, that's great. But that's usually the way that we're talking about. And especially for the final and the lab final, he's very big on odd man out. So what that means is that he's not a great test writer, and he doesn't understand that if one answer looks significantly different than the others, that's the one he's probably looking for. So usually that's an easy way to choose the right answer. Okay? I am not really like that, but that's okay. The other thing that I really want to talk about, and this has more to do with lab than anything else, I really don't like it when people come into lab and have no idea why they're staying in there. There's a purpose for you being in the lab, and it has very little to do with torturing you for more work. Lab is designed to give you some experience in not only working with the materials that we're talking about in the lecture, but hopefully make those more clear and concrete to you, but also because some of you, after having been in this room, will go into places where you need to keep a lab notebook. You need to be doing scientific investigations. And so it's important that you understand what those processes are. Right? I have had students in the past where I say, something's going on, and they ask me a question. I say, is that what you were expecting to happen? I don't know what I'm supposed to be expecting. And that just baffles me. Because if I've read the lab manual and I know what I'm supposed to be doing, then I should have some idea, based on what I've been told, what I should be looking for. So you should have some idea why you're there and what it is you think you're going to see. That is what we call developing the lecture and a hypothesis. So I have a hypothesis. I think it's going to go this way. I design an experiment to test if it's going to go that way. I collect that data, and then I see, does that data support the hypothesis that I made, or does it not? Now, if it doesn't, that's okay. That could be for two reasons. One, it could be my hypothesis is wrong, a perfectly acceptable answer to have, or it could be because something got screwed up in the lab, which happens a lot. It's okay for that to happen. What you need to be able to do is to be able to evaluate your work to say, was that potentially something that I or my group did? Or was that something that was a real answer that means that I had the wrong hypothesis? Because unlike what we do in this lab, in the real world, if you get an answer that says it doesn't support the hypothesis, you usually have to go back and test it again. You have to know if you need to set up that test in the same way or if you need to do it differently. So those are things that I have an expectation for. Questions about that? All right. Any questions about what I talked about so far? Like, are you ever going to stop talking? Yeah, eventually. All right. So, material from 110. You'll notice that there are some links that are in here. This is a link to this particular image. These are all through the textbook. So in case you don't remember that topic, you need to review it. You'll know where that is. these are the things that we're going to be talking about today. We'll start with periodic table, because the periodic table is it tells me everything I need to be able to answer almost any question. It's just a question of knowing how to associate that information with the table. A couple of things that we talked about last term, periodic trends. So, periodic trends always go in this direction. Effective nuclear charge. So, what is effective nuclear charge? As I move across one of these rows, I continue to add more protons into that group that I'm talking about, right? So as I add more protons to that, I add an additional electron, but it's all in the same physical space, right? So those electrons see all of those protons. That's very easy. But those protons don't necessarily see the additional electron. What happens then as you go across, you're still talking about that same physical size, is that effective nuclear charge, as it gets bigger, pulls those electrons in more. That's what we mean by it. So as we get higher effective nuclear charge as we go across, the atomic radius gets smaller. Higher charge means that we're going to pull things in more. So things on this side are bigger than they are on that side. So that's my effective nuclear charge. It also deals with my atomic radius. We can then talk about ionization. It's an ionization energy. It's the energy that it takes to remove an electron to turn that thing into an ion. That's what we're talking about. So if I'm going to take something off of that thing, we have to look at how much does it want that electron. How much it wants that electron has everything to do with how close it is to being a noble gas. These are my noble gases. Why are they called noble? Yeah, that's true. Very much true. It's because they don't do a lot of chemistry. And so everything really wants to be like that. Because they don't want to get messed with. Really, you want to be messed with? Typically, most of us don't. So everyone wants to be a noble gas. These particular guys have 2 s electrons and 6 p electrons, giving them a stable octet. So their outer shell is full when we get over here. And that means that they have no room to be messed with in that outer shell. So that's what we're looking to do. What that means is that if I'm on that side of the table, I want to throw away electrons to get to that stable octet. So it's easier for me to do that over there. That's why my metals over on that side tend to be positive. We know that this tends to be a +1. This is a +2. Again, because in my S here, I have 1 s electron, 2 s electrons here. So I will lose the 1 and the 2 in those areas. These transition metals can have lots of different charges. The only way I know which charge it is by the name that it has, or the formula that I'm given. So we'll talk about that when we get to the names. Over here, if we're on this side of the staircase, we're going to end up being positive. Because those are our metals. When we get to the staircase, those are our metals. So they can do both. It actually depends on which side you're on. So if you're on the right-hand side of that, we tend to pick up electrons to be negative charges. And do they always? It depends. What does it depend on? What kind of bond it is. Get to that in just a minute. So that's how we determine whether we're going to lose or gain electrons. The amount of energy that it takes to lose or gain that electron depends on how many I have to lose to get to that stable octet. Since we don't do the math with that, it's not important that you understand that. All that's important is that you know if it's going to lose or gain, because we need to know what those charges are. One of the other things that we talk about is electronegativity. So what is electronegativity? Electronegativity is when you're talking about a bond between two things, like H2O, right? We want to talk about how much affinity those two things have for the electrons that are in that bond. H is not very great at pulling electrons away. Br, on the other hand, has a great ability to pull those electrons to it. And so we end up with a bond that has an unequal distribution of electrons. And that's because of the difference in electronegativity. You'll need to know what the names of some of the groups are. So why do I say that? Because that tends to be why we ask questions. The ones that we need to know are the alkali metals, or coupling earth metals, chalcogens, halogens, and double gases. So those are the ones that you need to know. Because you may see a question on a test that says, I have an alkali metal down to a chalcogen. You need to know what I mean by that. You should be able to look at electron configurations. I will not specifically ask you to write one. That has a lot to do with the energies that we'll be looking at this term. Those electron configurations are a lot of why we see the energies. So you need to understand that side of it. That also is helpful in predicting your atomic charge. Okay? We also need to know how many valence electrons things have. Now, I'm not going to ask you to draw any of the Vesper structures. We don't need those here. Okay? Those are not as important until we get into organic. But it is important to know how many valence electrons there are. Because again, that will determine how many electrons I want to lose or gain to get to that 10. Question about that? Yeah. Okay. So, blank periodic table. Awesome. Where are the metals? Yeah. This side. Almost everything over here. Where are the metals? That's actually those things along the stairs side. And where are non-metals? Yeah, this little group up here, which is responsible for 90% of the compounds that we look at, which is a little strange to me, but okay, fine. Where would I see an increasing effective nuclear charge? As I go across this way, or as I go across this? That's right, that's left. We're going to see it getting higher as we go from left to right. What about our atomic radius, which is big?
Like,
These guys are big. What about our ionization energies? It takes more energy to remove electrons up on this side than it's up on this side. What about electron affinity? They get bigger as we go up toward the floor. These are key on that. And what about the electronegativity? It's actually the exact same trend as the electron affinity. Because electron affinity is for a singular element. Electronegativity is when it's balanced. So they're the same thing, just in different specific locations. All right, what's the name of this column right here? Column 1. Metals. What about column 2? Earth. What about 16 for those guys? 17 and 18. Yay! What ionic charge would we expect for a chalcogen? 2. So oxygen being a chalcogen, that is typically -2. Since he's right here, he wants to have 2 electrons to become like the nearest cats. What would I expect my ionic charge to be for a metal? +1. We will lose 1 electron to go back and be like the nearest cats. How many valence electrons would I expect in a halogen? 1. Valence electrons. So valence electrons refers to how many are in this outermost shells. So I'm talking about fluorine, which is this guy who's right here. I want to know how many are in this outermost shell. Okay. If we're talking about row 2, he has 2 s electrons, and then 1, 2, 3, 4, 5 p electrons. So he has 7 valence electrons. So 7. Remember that this is the p block. Sorry, S block. This is the P block. This is the P block. This is the F block. When we do our addition or electron configurations. So when we're talking about how many electrons do these things have, it depends on what we're talking about. if I'm talking about, for instance, Mg was on 12, his electron configuration would be 1s2, 2s2, 2p6, and then 3s2. See in that second row. So that's where those P's, D's, F's, all of that come in. We need to know where those groups are because, again, S and P are the ones that are responsible for that outermost shell, and therefore are the ones that are available. The ones that are available for us to demonstrate. Questions about that? I did say we were going to give some electron configurations, but I was going to have you do these on your own. I'm going to skip that for now. Cool with that? Like, yes, please stop talking. When we talk about types of bonds, there are two types of bonds that we typically talk about. There are things that we talk about within each of those, but there are two main types of bonds. What are they? Yes, covalent and ionic. When we talk about ionic bonds, what are we looking at? Yep, so we're talking about metal and non-metal. When we talk metal and non-metal, that means that we're going to have charges on both of them. So we're going to have an anion and a cation. Your anion is going to be your non-metal, your metal is going to be your cation. And therefore, we're going to have an electrostatic attraction between the two of them. What that formula looks like is based on what is the charge for each of these things. Okay, so that's we'll get to that in just a second. When we talk about, and do we share electrons when we talk about ionic bonds? No. So we have a complete electron transfer from our cation to our anion. So we're not sharing electrons. We've given them up. Cool. Awesome. When we talk about covalent bonds, what do we talk about there? Who's involved in a covalent bond? Two atoms, yes. And we're always talking non-metal to non-metal. So again, knowing whether it's a metal or not is important to know what kind of bonding we're talking. We are just talking about sharing electrons. The reason for that is that we can't either give up or gain enough electrons to get a stable octet without sharing. So that's why we do that. Those types of bonds are very different in terms of what they do. Questions about the two types of bonds? So we'll just pick a couple of random things out of this list. I'd like you to look at all of these later, but K2CO3. Covalent. Now, how do you know? Okay. So I love all of the answers that I'm getting. All right. What I look at when I see this, first thing that I see is an Na. What is Na? Metal and non-metal. If it's a metal, it has to be ionic. I can't have a covalent bond that includes a metal. Now, are there covalent bonds in that? Absolutely. The CO3 2- is all covalent bonding. So that answer is also correct. But it depends on which part of this that we're talking about. Now, CO3 happens to have 2 extra electrons, so it's a CO3 2-. How do I remember that? Well, because I've been doing this forever. This is your friend. What are these? On D2L, you'll find a copy of the exam habits. This is what you'll get on the test. You'll actually get one of these booklets. You're not going to get to bring your own, because then you can write whatever you want, and I don't encourage that. But this has a list of the polyatomic ions. Why do I do that? Because if it's a polyatomic ion, chances are it's not going to come apart. So we don't have to worry about it falling apart. We want to know if these things exist, because when I'm doing an equation with that, it's not going to come apart unless I specifically tell you it comes apart. In which case, whatever I do on the other side, I'm still going to have that CO3 2-. So that becomes important when we talk about that. So again, all of these polyatomic ions are going to be in here so that you have a reference for those. Okay. Do I recommend printing those to do with your homework, carry around for almost everything? Yeah, of course I would give them to you if I didn't think they would work. But the other thing I have to tell you is that Alex hates that information. It doesn't necessarily agree with everything as it's written. You'll find that that's more of an issue this term than it was last term. Because we start talking about energies and quantities for values, and mine might be a slightly different number of decimal places than what Alex has, and then Alex is going to freak out because you didn't use the right number of decimals. So you're thinking about these things. We get some later ones. And so that is an ionic bond. It's impossible. Let's talk about something else. H2O. What bonding would you expect in H2O? Well, that's an interesting question, though, isn't it? How would I know? So typically what we say is if it's a metal and non-metal, what the heck is hydrogen? Is that a metal or a non-metal? And it actually has characteristics of both. We can't characterize H as either a metal or non-metal. So hence why I asked the question, because I don't really know if that's an ionic or covalent bond. Right? One of the ways that I know that is because I know that H2O has the ability within water to become H plus and OH minus. But if it was ionic, it would all be H plus and OH minus. Because ionic compounds, when they go into solution, completely dissociate. But water doesn't completely dissociate when it goes into water. So it's not an ionic compound. And it actually has sharing of electrons between the H and the O's, which indicates that it is a covalent bond for the purposes that we're talking about there. Why do I mention that? Because water is weird. It doesn't behave like anything else. So when we're talking about the properties of water, they're usually very different than when we talk about living things. So that is the answer there is both. So don't freak out about things like that, because it does occasionally happen. And notice it kind of happened here too. We talk about nitrogen dioxide. Covalent, yes. Two ways that I know it. One, it's all non-metals. So that's the biggest. I also see that it's a nitrogen dioxide. That di in front of that indicates that it is a covalent bond because the nomenclature goes with a covalent bond. We'll remind you about all of that stuff in a few minutes. Questions of that? Now, I did give you lots of practice for these, and I will put up all of the answers for those so that you can do those on your own, either inside class or outside of class. We typically put them in there, and if we have time, we will go through them at the end of class. But we want to make sure that we get all the material so we don't necessarily do them all at one time. All right. Oh, names. I have to remember how to name stuff. Yeah, actually, it's more important that we be able to go from a name to a formula than it is to go from a formula to a name. Now, might you occasionally get asked what's the name of this thing? Sure, it happens. But it's more important that you be able to go from a formula to a name because, to be honest, how easy is it for me to write a formula compared to a name? I'm typing your text. It's easier for me to write a name than it is a formula. So a lot of times we see that things are very lazy. So that's something that we run into. Okay. Not gonna lie, kind of slow. So we need to be able to figure out from that formula whether it's ionic or covalent. And when we're talking about formulas to names, we also need to be able to do that before. Why do I need to know what kind of bond it is? Because the rules for the two classes are different. Okay. When we look at nomenclature rules, this is one of the things that we can do when we talk about it. You'll notice that there are two specific things that are listed here, ionic and covalent. We also talk about acids. You don't need to know how to know the name acids. That is not something we've asked you to do. And it's not something we will be doing this term either. But ionic and covalent, we do need some. When we look at that, we know we've been talking about it. Covalent compounds are not ionic. So all non-ionic, or sorry, non-metals, all non-metals. Whereas ionics are metals and non-metals. The rules for naming those things are different. So we need to make sure we know which one we're talking about. So how does that apply? What do we mean? Well, let's name the following formulas. We'll pick two of these. Pick whichever one you want, and we'll go with it. SO3. Okay. How would you name it? I gotta ask, what's that scope? Sulfur. Hey, what's up? Oxygen. Now, am I done? Not quite. So I know I have to have sulfur, and I write that first because that's the first thing written in the formula. I then write the name for oxygen, but it doesn't just say oxygen. It gets changed a little bit. What does it get changed to? Well, it is a tri. So the first thing is it becomes an I because it's the second thing you write. So first it's an I. And it's a trioxide because it's a non-metal bond. So we have to indicate how many of them there are. Because it could be SO2, it could be SO3, it could be SO4. So we need to know how many of those oxygens there are. The only thing that you don't need to do is put a number out in front of that sulfur. Now, is it acceptable to say that it's a monosulfur? Yes, absolutely it is. But it's not required because it's the first thing. So that is off from it. We'll pick it out. One more.
ALF3.
ALF3. Okay, awesome. All right. ALF3. What's AL? Aluminum. What's F? Yes, it is a fluoride. And that's a metal to non-metal. So do I have to name it as a trifluoride here? No. And that's because Al is only a +3 charge. F is only a -1 charge. There is only one way that those two things can come together to make a formula. So the rules for the ionics do not include telling you how many there are. That's all based on the charge. Let's go the more important direction. And let's talk about silicon tetrachloride. So what's silicon? Silicon is S. And of course, the periodic table you get on the test has both the formulas. That's an SI. Tetrachloride is which element? Yeah, it's a chloride, so that's a Cl. And tetra, so there's 4 of them. SiCl4. And since it's a metal to non-metal, I know that that is the way that goes. Cool. Of course, I covered up what I was trying to talk about. Go me. Let's talk about magnesium phosphate. So magnesium phosphate. Magnesium is which one again? Mg. And phosphate is what? Yes, it's AP. Oh, the faster I go, the worse the handwriting gets. And that's a 3-. I know that phosphate is one of these polyatomic ions. I know that it's always 3-. Yay, awesome. Since it's a polyatomic ion, that probably indicates the first thing is a metal, which it is. Mg is an alkaline earth metal. Mg being an alkaline earth metal has what charge? 2. So if he's a 2+, how am I going to make this a neutral formula? Yes. So what I do is I take this charge right here, and that becomes the number that comes for the Mg. For the Mg, I need 3 of them. And the PO4, I need 2 of those. Because that means that I have a +6 and a -6 in terms of my charges. It means that that is at -0, which is exactly what I need. So we need to make sure that we're looking at charges for our metal to non-metal and looking at how many of them there are for our covalent compounds. So metal to non-metal. Questions about that? The only weirdness you will see is that when we talk about our metals who have been transition metals, we'll see something that looks like this. Chromium or oxide. Why does it say that?
Because it's the chart on the chromium.
Exactly. Since chromium is a transition metal, you can have multiple charges. There are two common charges for chromium. One is the 2+, which for transition metals, 2+ is always good, because they can lose the 2 s electrons that are there. So the ones that come here, scanning, we can lose those 2 s electrons to become a 2+. It can also lose those 2 s electrons and the 1 d that it has to become a 3+. So there are multiple charges that it can have. And the only way we know which one it is because the name says so. Each one of the names for something that is a transition metal should indicate to you what that charge is. I will be honest, sometimes I forget. So if you don't know and you need to know, ask me, it happens.
So that would be Cr4O.
So chromium 4 is Cr4+, and then it's an oxide, which is O2-. And so that's going to be a CrO2. If I multiply the 2- by the 2, that gives me a total of 4-, which then gives me the same as 4+. Questions about that? Now again, you will not be penalized if you do not know how to go and get a formula for this. All right. Will I tell you what it is on a test? Absolutely. Of course I will. Will I make note that I had to tell you? Yeah, probably. And you might lose like half a point for me having to tell you. Bummer. So, but that is a thing. Why do I do it that way? Because Google is your friend in real life, but not on your tests. So, questions about getting from names or formulas? I'm just going to have you do a little bit more. Now, it's almost 9 o'clock. Do peeps want to take a break? You guys need a moment? If you don't, that's cool. But if you do, I don't want to torture you. So what are we going to talk about now? Oh, Lord. Chemical reactions, concentrations, and stoichiometry. Ooh, yay. This will be fun. So chemical reactions are required to understand how much of what needs to go together, but that isn't important that I know what those things are. Absolutely. Why is it important that I know what the balanced chemical equation looks like? Because all of my math depends on the chemical equation. If I have an unbalanced chemical equation, like if I looked at this and didn't have these numbers out, and I were then to talk about a mass of Na3PO4, which I then convert to moles, and then once I've converted it to moles, ask you how much KOH I need either in terms of mass or moles. That answer would be wrong if I didn't know that over 3 times as many KOHs were required as the Na3PO4. So that's why that matters. That molar ratio is really important for stoichiometry. So we need to make sure that that's what that means in terms of what you need to do is you need to make sure that whatever species you have has the same number on the left side and the right side leaded up. So this is the way I do that. I won't say, well, I say, okay, this is what I start with. I have Na3 on this side. And on the other side, when I initially write my NaOH, I only have 1. I know that's not going to work, so I have to cross out 1 and give 3, because that's the only way I can make that balance. Once I get that, that means I then have 3 OHs on that right-hand side, but I only have 1 on the left-hand side. So I'm then going to have to multiply that by 3, which then takes care of the 3 Ks that I need because I get 3 here. So make sure that you're balancing that for mass, and that's what we mean by that term. Balance for mass is the same for both sides. We also have to start looking at charge. So when we do things like ionic compounds, we know that we need to determine K3PO4 because a PO4 is a 3 minus, K is a +1. So it needs to be a K3PO4. That means that overall that has no net charge. But this term will have equations that have charges on both sides. We need to make sure that they're the same on both sides. So that's the other thing I need to check is the charge. Make sure that I have the same charge on both sides of that equation. Questions about that? Oh, concentration. What is the most common concentration we talk about? Molarity. Molarity is used almost all of the time. And the reason we use molarity is because we can calculate, we typically measure the mass that we put in, we can calculate the number of moles, and we know the volume of the solution. Okay, awesome. I can't always use that. Why not? Can you think of any reasons why I couldn't use that? The one that always stands out in my head is molarity is temperature dependent. Why is it temperature dependent? Because the volume of that solution will change as the temperature changes. The density of that thing changes as the temperature goes up, takes up more space, therefore we have a different density. So if we're talking about temperature changes, like for freezing point suppression, boiling point elevation, we have to deal with something that doesn't have that. So instead of looking at a volume, we look at the mass itself. We use molality because that's temperature independent. So that's the most common time when we talk about molality, because that's a mass per mass. Occasionally, we don't necessarily have other things. Lots of stuff will give us a percent by mass. So we'll say it's 3% by mass for this particular solution. We need to be able to convert from that percent by mass to things that are going to work for us, what we typically won't. We also occasionally have to work with mole fractions. Our mole fractions come in most often when we talk about gases. If we're looking at the partial pressure of a particular gas comparative to the total pressure, then we need to be able to talk about the mole fraction. So these are all of the units that we typically see at this point. You should be able to convert between the two. 3, 4 of them. But molarity is the one that we work with the most often. We can convert from a mass to moles. Once we have moles, we divide by the mole. Okay? Questions about our concentrations? And this is one of these questions that I absolutely love. So we can talk about commercial vinegar being essentially a solution of acetic acid and water, because that's what it is. Bottle of vinegar has a 3.78 grams of acetic acid per 100 grams of solution. If the density of that solution is 1.0 grams per milliliter, acetic acid has a molecular weight of 62.05, we can calculate the molarity, the molality, the percent by mass, and the mole fraction. In order to do conversions between these things, typically we'll need density to be able to do that, because we need to know what the mass per volume is to be able to make those calculations. The only other weirdness that goes on with this is you need to know how much of that is solution versus solvent. So if I have a solution that's made by putting 3.78 grams into 100 grams, then that mass of the solvent is 100 grams. The mass of the solution is 103.78. So there is a slight difference there. So we need to make sure that we're aware of that. So that's where weirdness comes in. Questions about any of that? You most often have to do these kinds of conversions in the lab, not actually in the, like for tests, but that is something that we typically see in the lab, because we will occasionally buy stuff that only has a mass percent that we're given. Okay? Oh, stoichiometry. That was a big, huge word, and it's one of my favorites. What the hell is stoichiometry? Stoichiometry is the fancy name that we give to doing calculations to determine how much of another species we're dealing with. So if I know the mass of something, I can calculate the number of moles by dividing by the molecular. Fairly simple. Once I know the number of moles of that particular substance, then I can tell you how many moles of another thing it has to react with, or another thing that's going to be produced from it. That's typically what we're looking at. It's a very practical thing. Because if I'm working in industry and they tell me you need to make 5 kilograms of this material, then I need to know how much I have to start with to make that happen. Happens all the time. So stoichiometry is how we do that. Now, are they always mass to moles to moles to mass? No, those are the most straightforward, but they're not. We can also talk about going from the volume of a solid using its density to get to the mass. We can talk about the volume of a solution, liquid. If we know what the molarity of that is, then we can get to moles. That all the time. We can talk about the number of particles that something is. Or once we've calculated it, convert and tell me how many particles there are in that by using some. We can also talk about the volume of a solution of a gas. If it's a gas, and I know how many moles it is, then I know what its pressure is going to be, and I know what its volume is. So all of those things are possible. We just need to remember how they work. For assistance with that, this image is in your exam. So you can remember that there are ways to get between them. And if you look at the little text in between, it'll tell you what you need to get between the two. Okay? So that's our stoichiometry. Do you need to do stoichiometry in this class? Oh yeah. That's almost all of what we do. Okay? Here is an example of doing some stoichiometry. I am reacting silver iodide with iron 3 carbonate to produce iron 3 iodide and silver chromate. 12.334 grams of iron 3 carbonate and 26.5474 grams of silver iodide are added to 1 liter of water. What amount of silver chromate is produced in terms of moles, molecules, and grams? Do I typically torture you with that on a test? No. I will ask you how much is made. Does it mean that you have to tell me that answer in all of these things? No. If I don't specify what the answer needs to be, I don't care what you choose. Because they're all relevant and they're all valid. If I ask you to tell me how many grams, you better tell me how many. When we do this, I started with the amount of Fe2CO3 that I have, the 12.324. I convert that to moles of Fe2CO3. I know that there's 1 mole of Fe2CO3 or 3 moles of Ag2CO3. And that tells me how many moles of Ag2CO3 are produced from this component. Now, why did I say from this component? Because once upon a time, we talked about something called limiting reagents. So it is possible that that amount may not actually be what you can form. You would have to do this calculation for this amount too to see if that number is lower. It's the only way that I can verify how much I actually produce. The calculation is set up the exact same way. Now, are you expected to do that? We tend to set this up in such a way that I say, you have this in excess, and therefore you know which one you need to deal with. Just to make life easier and not as complicated on the example we're taking. Okay? I can also do the same setup for this, but instead of just going to moles, I can then multiply by the molecular weight of Ag2CO3 to get the grams of Ag2CO3 that I have. And if I want to know how many particles or how many molecules of that material I have, once I get to the moles of Ag2CO3, I can multiply by Avogadro's number to tell me how many molecules of that material that I have. Okay? Questions about our stoichiometry? Okay. So now we're going to talk about dissolving in water. One of the things that we talked about, when ionic compounds dissolve in water, they completely dissociate. That's what we used to tell you. part of what we're going to talk about this term is that that's not actually true. And from a practical standpoint, you probably know. How many of you had sweet tea? And how many of you have gotten sweet tea that has sugar sitting in the bottom? Why is that? Because not everything will dissolve as much as we want it to dissolve. So there's a point where there is too much solid for it to go into solution. That point is dependent on some things that we'll talk about later. But that does mean that there is a practical limitation to how much we can get into solution. Now, some things dissolve and they stay together. Some things dissolve and they come apart. When glucose goes into water, does it come apart? No. Why not? It's not ionic. Yes, it's the exact answer that I was looking for. So glucose is C6H12O6. It's not an ionic compound. It's not an ionic compound. It doesn't dissociate. It dissolves, but it does not dissociate. That means that for every one that I put in, I get one out. If, on the other hand, I dissolve NaCl, do I still end up with the same number of NaCl's as I do NaCl? What happens when NaCl goes into solution? It does dissociate. That is correct. So let me see if I can find myself some space. That is not what I wanted to do. I don't like this whiteboard, but until I'm able to do the other thing, I don't have to work. So when we talk about NaCl going into solution, I got rid of my pen. There we go. Sorry, brain. NaCl. I know that this is made up of Na ions and Cl ions. So when this goes into solution, I end up with an Na plus and a Cl minus. So for every NaCl I put in, I get two things out of it. We call that thing a Van Hoff factor. It's labeled as an I when we talked about things like boiling point depression, freezing point elevation, that kind of stuff. And so the fact that it comes apart and makes different particles is important for us to understand. How many things it comes apart to is also important. Because an NaCl gives us two things. An Mg3PO4 gives me 5. Because there are 3 Mgs and 2 PO4s, so that's a 5. So things that have higher charge tend to give us more particles when they go into solution, and therefore are better at raising boiling point or lowering freezing points. So if I'm going to drop something in my driveway in a place where we actually get driveway freezing, here, we want to do that with something that has more than 2 particles. It becomes, when it does, CaF2 is a common thing to do because it's not corrosive. And we end up with 3 particles, which is a better force for the parts. Okay. Questions about that? So do I need to know what it comes apart to? Absolutely I do. Why do I need to know what it comes apart to? Because then I can determine what kind of forces are going to exist in that solution once that happens. We talked about a number of different forces. There's hydrogen bonding, there's ion dipole, there's dipole-dipole, and there's van der Waals. Everything has van der Waals. So that's not something I ever really consider because it's with everything. But in order for me to be able to determine if they're going to be dipole forces, I need to know what that thing looks like. And so in that case, I need to be able to draw its Lewis structure to see if it has a dipole. In order to be able to determine if it has hydrogen bonding, I need to know if there's a hydrogen in that molecule. It's not an oxygen, a nitrogen, or a fluorine. Because if there is one of those, there's not going to be any hydrogen bonding. If we want to talk about ion dipole interactions, water has a dipole. So anything that dissolves into it and becomes an ion it's going to have an ion dipole interaction. Those interactions lead to higher forces, right? More interactions means that I have more things to break, which means I need more energy to be added to that thing to get it to do stuff. That leads to things like lower vapor pressures for those things because they need more energy. So we typically have lower vapor pressures, higher boiling points, lower freezing points. Again, all of that because we have those structures we have to disrupt. It also affects the osmotic pressure. Any of our colligative properties are affected by those changes in forces. Okay? So that becomes some of the other things that we have to think about is when we get things that dissociate, now that they're dissociated, they're available to do chemistry. Oh, now, do things that don't dissociate do chemistry? Yes, but they're not as likely to. But then we need to be able to think about what else can it do. So one of the things that we talked about last term is solubility, right? We know that some things are not soluble. So if I make a Cl minus when I dissolve my NaCl, and then I introduce silver into that thing, Ag plus Cl minus makes AgCl solid, which drops out of solution. It's important to understand that when I mix those two solutions together, I'm going to form that solid, and that's going to happen. So if I wanted to do something that involved both of those ions, they're no longer available for me in chemistry. So one of the things that we'll talk about this term is precipitation. So that formation of that solid and how much of that happens, how we can affect that, how we can change whether it does or doesn't occur. That goes. We also need to know what that concentration is. Okay? Because if I want to do chemistry, I need to know how many of those things I have available. Okay? So, questions about that? Talked about that. And I actually talked about this too. So the properties that we typically look at: vaporization energy, vapor pressure, freezing temperature, boiling point. More resistance to flow, the more interactions I have within that solution, the more resistance to flow it's going to be. Capillary action is affected by these things, and surface tension is affected. The higher the interactions in the molecules, the more difficult it is for that surface to break away, i.e. leads to lower vapor pressure, higher boiling point, but also then leads to a higher surface tension. Okay. Questions about any of that? Three more topics. And then you will be done for torture for now, at least until lab starts. So we need to be able to talk about gases. Why do we need to be able to talk about gases? Because I said we did. And because we might have something in the gas phase. If it's in the gas phase, we need to know how we can do chemistry with it. When we talk about gases, as opposed to our solids and our liquids, we need to be much more aware of the conditions that exist around it. So temperature, pressure, things like that affect the volumes and the number of moles that we see. Okay. So if I want to have nitrogen gas react with hydrogen gas to form ammonia, or a process, this is how ammonia is actually made in the real world. We do that at 425 degrees. Now, there are reasons for why we choose that temperature. We talked about those reasons for that this term. It reacts by N2 plus 3H2 goes to 2NH3. Cost of nitrogen gas is very high. It is, which is ridiculous. It's not true. But it should be ubiquitously available, but it's not. It is extremely expensive right now. And of course, the N2 is now more expensive than the H2. So that's going to limit how much of that I can purchase to make this happen. But if I still need to produce 25 atmospheres of NH3, I need to know the minimum amount of N2 that's required to do that. So I can go through this calculation. Okay, I need 25 atmospheres of NH3 using PV equals nRT, gas equation. I can set that out to solve for N. So 25 atms is my pressure, 698 is the Kelvin temperature, 50 liters is the volume of this vessel that I'm looking at. And I divide by R, which is 0.0821 liters atmospheres per mole Kelvin. And that will tell me how many moles of NH3 are required if I want to produce that 25 ATM. Once I know how many moles of NH3, I then have to look at the mole to mole ratio. Because if I have NH3, there are 2 moles of NH3 required for every mole of NH2. So I get twice as much NH3 out of it as I need the N2 to put in. So I have to divide that by 2 to determine how many moles of N2 are required. Once I know how many moles of N2, I can go through PV equals RT again to figure out what that pressure is. Now I have my N here for N2, my temperature, my volume, and my R, PV 12.5 atmospheres of N2 required. Cool with that. Now, a couple of things that we see when these things happen. We're not always at the same temperature volume conditions afterwards as we were before. So we don't always get nice math like this where it's exactly a half. Okay. The molar ratio is not the only thing that typically happens with this. But those are things that we need to be able to talk about. So calculations in terms of PV equals nRT and P1V1 over N1T1 equals P2V2 over N2T2 are going to be relevant to some of the things you have to do. Okay? All right. Now what? Well, the next 2 things we were supposed to talk about were acid base and precipitation reactions. These were 2 of the topics that we talked about. We talked about them a little bit today. We are going to talk in extreme detail about precipitation reactions and how we can affect those this term. So we're not going to worry about that anymore today. We're also going to be talking about acid base for 3 lectures. So we're going to talk about that, right? But that is a preview of what we're going to be talking about. In terms of lectures, the next one is going to be chemical equilibrium. We have to talk about that first to be able to talk about the rest. Then we'll talk about acid-base properties for 3 lectures. And then we'll be talking about precipitation and common ions, and that will take us through the first test. Now, as far as tests go, will you know what's going to be on every test? Absolutely. So everything is set up in D2L for exam 1, exam 2, and exam 3. We will do the first set of lecture for exam 2 before we take exam 1. That gives you additional time to try and assimilate that information before we take the test. Does anybody have any questions about any of the crap that I threw at you today? We will have a lab introduction this afternoon at 11:30. Whatever. But we'll go through the introduction for lab. We'll talk about what is required and it's going to be safety goggles and the lab notebook. If you have a lab notebook from last term, that's fine. You can use it again in terms of what I want in it. That may be different than what you did before, so we'll talk about that. We'll talk about general safety, that kind of stuff, and what's going to be doing for lab. Questions on the lab stuff is going to be questions, comments, probably. Yeah.
So for every lecture, we will discuss.
Every lecture will be in here, every lab will be in a few seconds. And I am available if anyone wants to talk to me. I need to talk to you for just a second. What's your name? In terms of, so why do you think it's spots? Just for my information. I love that stuff. Sorry, I'm getting here's my bottles. What do you want to transfer to? Again, here it is. I asked everybody else to define themselves in one word. So my word is stuff that I can do stuff. But I got things like patient, perceptive. Some use that are 90%. understanding and stuff like that. So if you had one word to define yourself, what would
That's what I'll say, perceptive.
that is perfectly fine. It gives me some information about who you are and what it is. Also, how comfortable are you with math? Again, some people are math people, some people are not. So I like to know ahead of time which I should approach with.
Excuse me, I just took count of
Okay. That's all the torture I have to use. Well, for that.
I'm sorry, I was late. There was really bad traffic and the door was open in front of the building, so I panicked and I thought it was either the wrong building or the one. So
Which door?
the sliding door.
They had not unlocked the slide, but I hated to do that because to do it, unfortunately, a lot. So
And you wanted a composition for the lab.
something back. That's all that matters.
Question.
Of course.
So I am unfortunately having to take organic chem at the same time.
Hooray!
I guess they don't offer it in the spring too. They only offer it spring one online.
We only have so many students. Yes.
So do you think that I'll survive both classes?
It's going to be a stretch. I will propose. Are you with Sison or Twinton?
I think Sison.
He's a really great guy. He works with my husband.
Okay.
He's really amazing. So, but don't worry. If you have questions and you can't get a hold of him, who actually section yet? Professor Twinton.
Oh, no, I'm with her.
Oh, you're with her.
Yeah.
She's amazing.
Okay.
Organic was what she studied in grad school, so she's really, really good with it.
Okay.
So, and any questions you have, she'll be more.
Is there any overlap that I should be concerned about? I've taken it before and I did okay in it, but I remember having to study a lot.
Yeah. There's not a ton. No. So the majority of what we need out of Gen Chem for organic is the structures, so the root structures and things like that. You've got that. As far as there will be some discussion about like thermodynamics and how favorable is this reaction. That stuff we're going to be talking about this term. But if you've seen it before, it shouldn't be that bad.
Okay. I mean, it's been 10 years, but.
Yeah, but I was totally surprised by how much organic I remember when I sat there. And, oh, I should do remember.
Okay. Yeah.
It's probably not as bad.
Okay.
But if you run into any issues, let me know.
Thank you. I'm worried about taking it online, to be honest, but let's see.
But what choice do you have?
I don't have a choice. I have to take it either now or
Has she made any of her recorded lectures available?
I'm sure she has. I'm just kind of focusing on this class first, and so when we don't have class, that's my organic day.
Yeah,
I know
how that works. Yes. Yeah. But yeah, like I said, I have actually taught I haven't taught the lecture for that in 8,000 years, but I do the lab all the time, so the concepts are not. I'm not great with remembering what reaction of things are because it makes like somebody says the name of a reaction and I get it. Just the whole idea freaks me out. Okay, well hopefully I won't get too freaked out. it's a lot of memorization. So biology is a lot of memorization. I hated bio. So going into organic, I had issues with one, the memorization.
Yeah.
And two, I have a very difficult time seeing things in 3 dimensions. And so it's really hard for me to understand backside attack, what this thing looks like. But it's my understanding that there are 3D modeling systems that work with now. See, that we had like these little model kits,
Yeah, that's what I had.
but they wouldn't let me use them on the test.
Right.
And I'm like, well, what's the
What's the
point in
point?
having it?
Got these dark triangles and
Yeah.
yeah.
I remember.
Okay. Okay. Well, if you think that I can do it, then
I think you'll be fine. So again, the most important parts of the structures which you have, the dipole interactions, the polarity of the bonds is a big deal because you're starting to understand why this thing comes apart the way it does. Yeah. I think you'll be fine.
Okay.
The majority of what we talk about here is very physical based.
Yeah.
And that's not.
Yeah, I mean, I'm so glad that you're the professor for this course. I told my dad, I was like, I don't think that I could have worked out any better. Because I've never understood chemistry like I do now.
Well, and that's good.
Yeah.
See, that's good. I mean, I hate to say it, but I did notice that people that were in my class last term seem to remember a lot more than you.
Yeah.
Either that or you guys are more comfortable talking in front.
Yeah.
And it could be.
Hopefully that'll benefit me at the end of class too.
I think that it will. Okay. The better your foundation is, the better your ability to stretch that.
Okay.
All right.
And thank you.
You're welcome.
See you in lab.
Yay, it'll be fun.